In July 2025, history was rewritten again. NVIDIA, the company founded by a leather jacket-wearing Taiwanese American, saw its market cap blast through the $4 trillion ceiling like a rocket, leaving every traditional giant in the dust and becoming the undisputed center of gravity in global capital markets. Applause, awe, bubble warnings, and skepticism all erupted at once. Headlines were consumed by Jensen Huang's quotes, staggering wealth effects, and the grand narrative of AI devouring everything. But for every decision-maker living inside this industry wave, investors, corporate strategists, technology leaders, the real question matters far more than a stock price moving up or down. What is actually holding this enormous empire together? Is it the GPUs that everyone is scrambling to buy, when AMD, Intel, and every major cloud provider all claim to have their own AI chips? Why does NVIDIA's throne look so unassailable, and after $4 trillion, how does the growth story continue? To find answers, we used what might seem like an old-fashioned method, but it's still the most effective one. We tapped our deep Silicon Valley expert network and spoke with several anonymous insiders on the front lines of the AI arms race. A former head of AI infrastructure at a top-tier cloud provider, a chief AI architect leading large model training, and a senior venture capital partner who has been reading technology bets in Silicon Valley for 2 decades. What follows is what they told us. This is not just a breakdown of one company. It is a deep analysis of the core forces driving an entire era. The answer nobody expected: it's not the chip. When we asked nearly every expert we interviewed the same question, what is NVIDIA's most important competitive moat? Not one of them said chip performance. Every single one pointed to the same thing: a piece of software created nearly 20 years ago called CUDA. A senior technical director who spent years building AI platforms at a major FANG company opened the conversation with a vivid analogy. The biggest misconception the outside world has is that people still think of NVIDIA as a hardware company. That's like believing Coca-Cola's success comes from the bottle. From the moment Jensen Huang formally launched CUDA in 2006, he wasn't selling chips. He was preaching. He built what amounts to a cult, the NVIDIA cult, and CUDA is its scripture. Today, when any customer buys an H100 or a B200, they're not just paying for silicon. They're buying a membership ticket into that ecosystem. It's an invisible tax, and almost everyone has to pay it. CUDA, which stands for Compute Unified Device Architecture, is where every NVIDIA myth begins. Back when GPUs were still just beloved toys for gamers, Jensen Huang made a visionary and enormously expensive bet. Open up the GPU's core, its thousands upon thousands of parallel computing cores, to general scientific and commercial computation. He played that long game for nearly 20 years. CUDA is not a product. It is an ecosystem. It encompasses not just a programming interface, but a complete suite of highly optimized mathematical libraries: CUDNN for deep neural networks, CUBLOS for linear algebra, along with powerful compilers, intuitive debugging tools like NVIDIA Insight, and a massive global developer community. It created the textbook case of a network effect. The more developers use CUDA, the more CUDA-based applications and frameworks get built: TensorFlow, PyTorch, and many others. Those killer applications then attract more users and more developers back into the CUDA ecosystem. Once that flywheel starts spinning, the gravitational pull it creates is enormous. Today, more than 4 million developers worldwide use CUDA. Almost every AI doctoral student's first lines of model code run on CUDA. That builds a powerful kind of muscle memory, spreading from academia into industry, cementing CUDA as the de facto industry standard. The invisible cost, the visible wall. We put a direct challenge to the chief AI architect who leads large model training at a major company. If CUDA is so dominant, why can't competitors like AMD's ROCm or Intel's OneAPI just build something better and replace it? He smiled and answered with a question of his own. Do you have any idea what it would actually cost to migrate a top-tier company's core AI business from the NVIDIA platform to another platform? It's not the hardware cost of buying tens of thousands of new chips. It's a bill of technical debt so long it makes you despair, and the total can easily be several times the hardware cost, or more than 10 times. He walked us through what that bill actually looks like. First, code rewriting and migration. This is not a simple find and replace operation. Countless engineers have spent enormous effort writing computation kernels hand-optimized for NVIDIA GPU architecture at the lowest hardware leveled on AMD or Intel chips. Virtually all of that code has to be rewritten from scratch. The differences in underlying hardware architecture are far more complex than most outsiders can imagine. Second, Performance optimization hell. Even after a successful migration, new hardware does not deliver NVIDIA equivalent performance out of the box. Engineers spend months, sometimes years, doing tedious performance tuning and chasing unexpected bugs, just to slowly approach the efficiency they had before. In an AI race where every hour matters, that time cost can be fatal. Third, the toolchain gap. NVIDIA provides mature, battle-tested performance analysis and debugging tools like Insight and NVProf that help engineers pinpoint bottlenecks fast. Competitors' toolchains still lag by years in stability, usability, and feature depth. As the architect put it, a problem you can solve in an afternoon on NVIDIA might take a week on another platform, and you still won't know where the issue actually is. Fourth, the talent shortage. The brutal reality is that the number of engineers who genuinely know CUDA deeply may be 100 or 1,000 times greater than the number who know ROCm. For any company, that means higher recruiting costs, longer training cycles, and enormous risk of project delays. Fifth, ecosystem inertia. On model hubs like Hugging Face, the overwhelming majority of open-source models are pre-trained and optimized for NVIDIA GPUs. When a team wants to quickly validate a new idea, the fastest path is always download the model, run it on an NVIDIA GPU. The architect's conclusion: NVIDIA's moat wasn't dug by NVIDIA itself. IT was built over the past 15 years by millions of developers worldwide, one line of code at a time, one debugging session at a time, one project at a time. Filling that moat doesn't take money. It takes time and an equally large and equally loyal developer army. Nobody can do that right now. From selling shovels to selling the gold mine. If CUDA is NVIDIA's software soul, its hardware evolution strategy is equally intelligent. A Silicon Valley venture capital partner with 20 years of experience offered a distinctive business perspective. To understand NVIDIA's business model, you can't just look at the GPU, you have to look at how its revenue per customer has climbed, step by step. This is a textbook case of upward integration. It's not fundamentally about selling products, it's about continuously solving bigger, more valuable problems for customers. He described NVIDIA's strategy as a 4-stage rocket. Stage 1, selling the part, the GPU chip. This is where it began. From the G80 to FEMI to today's Blackwell architecture, NVIDIA has consistently maintained single-card performance leadership. This is the foundation of everything. Stage 2, selling the machine, the DGX and HGX servers. NVIDIA quickly realized that customers don't actually want 8 individual GPUs, they want one beast that makes 8 GPUs work together at peak efficiency. Through high-speed interconnect technology like NVLink and NVSwitch, NVIDIA bound those GPUs tightly together and launched the DGX server. IT was no longer selling parts, IT was selling an AI supercomputer in a box. Revenue per customer jumped from thousands of dollars to hundreds of thousands. Stage 3, selling the production line, the super pod cluster. When customers needed to train models with hundreds of billions or trillions of parameters, a single DGX wasn't enough. NVIDIA used the InfiniBand high-speed networking technology it acquired through the Mellanox acquisition to connect hundreds or thousands of DGX servers into a massive cluster and wrapped it in a complete software management stack. That became the Super Pod. NVIDIA was no longer selling machines, IT was selling a complete blueprint for an AI model factory. Revenue per customer surged to tens of millions or hundreds of millions of dollars. Stage 4, selling the factory itself. Data center level solutions. Today, NVIDIA is moving toward its ultimate form. IT partners with cloud providers to offer DGX Cloud, where customers can rent a complete AI factory on demand. IT even participates directly in customers' data center design. What it's selling is AI capability itself. Through this layer-by-layer integration strategy, NVIDIA transformed itself from a chip supplier into the general contractor for its customers' entire AI strategy, the provider of a full-stack solution that no one can do without. Each integration layer solves a deeper customer problem and delivers higher margins and stronger customer lock-in. The next frontier, sovereign AI. The story is already extraordinary, but for a $4 trillion empire, the ambition goes further still. Take NVIDIA AI Enterprise, or NVIDIA. IT functions like the Windows operating system of the AI era. After customers buy NVIDIA hardware, they can subscribe to NVIDIA to get the stability, security, technical support, and performance guarantees they need to run critical workloads. This opens an entirely new, high-margin software subscription business, and more importantly, it converts the customer relationship from a one-time transaction into a long-term service partnership. And when that full-stack capability Hardware plus software plus services is refined to its highest form. It maps perfectly onto one of the most important emerging trends of the 21st century. Sovereign AI. An expert focused on the geopolitics of technology laid out what he called the final chapter of the NVIDIA story. We are entering the age of sovereign AI. Every nation on Earth will come to understand that having its own independent AI infrastructure, its own foundational large models, and AI trained on its own national data is part of 21st century sovereignty, as important as having its own currency and its own military. And who can provide the complete toolkit for building that sovereign AI? Today, the answer is exactly one company, NVIDIA. This pushes NVIDIA beyond the boundaries of a commercial company. Its products have become strategic resources in 21st century geopolitics. It opens an entirely new market measured not in customers but in nation-states and elevates the certainty and irreplaceability of its business to a level that has no historical precedent. $4 trillion. This number is not mythology. IT is not a bubbled in an era of information overload and deafening noise. Being able to see past the surface and understand the deep forces driving an industry is far more important than chasing daily stock movements. That understanding is the prerequisite for precise investment decisions and the foundation for long-term corporate strategy. The office building with the lights turned off 1996. San Jose, California. A cheap office building. The lights in the hallways are off. Not because they're broken. Jensen Huang had the building's voltage reduced to save on the electricity bill. The company didn't have enough money to pay both the utility bill and the payroll. He had to choose one. He chose payroll. At that point, NVIDIA was a company that all of Silicon Valley was laughing at. Their first product sold 250,000 units and 249,000 of them came back. Sega was leaving. Customers had moved entirely to competitors. Engineers were quietly looking for other jobs. The cash in the bank would last less than a month. Nobody believed this company would survive. 30 years later, NVIDIA's market cap surpassed $4 trillion, larger than Apple, larger than Microsoft, larger than the GDP of more than 180 countries, almost every machine on the planet. Training an AI model has an NVIDIA chip inside it. What happened between that dark hallway and today? 1992.3 people drew the future on a Denny's napkin. The story starts in a chain restaurant. Late 1992, a Denny's diner on the east side of San Jose. Jensen Huang sits across from two friends, Chris Malachowski and Curtis Priam. All three work in tech. All three believe they can see something the rest of the industry is missing. Their thesis: the standard processor, the CPU, is fundamentally ill-suited for graphics computation. It's a generalist. And generalists aren't fast enough at any one thing. Games, rendering, large-scale parallel computation, these don't need versatility. They need specialization. They need a dedicated chip. Jensen is 30 years old, working in chips at LSI Logic. He's the kind of technical manager who speaks directly and thinks in numbers and architecture. He immigrated from Taiwan, put himself through school on scholarship, and has spent nearly a decade in semiconductors. He's not the kind of person who moves an audience with passionate speeches, but he has a near-fanatical conviction about one thing: parallel computing is the future, and nobody is building for it. The three of them sketch diagrams on a napkin, talk through products, markets, and fundraising. In April 1993, NVIDIA is officially incorporated. First product, 250,000 units shipped, 249,000 returned. It was the loudest era Silicon Valley had ever seen. The PC revolution was in full swing. Microsoft's Windows had taken over every desktop in the world. Intel chips were inside more than 80% of all computers. Video games were making the leap from flat pixels to three-dimensional worlds. Doom, Quake. These games made an entire generation of young people realize that a computer could do something fundamentally new. NVIDIA's first chip was called the NV1, released in 1995. The design philosophy, viewed from today, was a kind of visionary aesthetic ambition. Jensen's team didn't want to build the 3D world out of triangles. They wanted curves, smoother, more realistic, more textured. The technical reasoning was sound. But there was one fatal problem: Microsoft disagreed. In 1995, Microsoft released DirectX, a graphics standard for game developers. DirectX required triangles. Full stop. Every game had to be written on top of triangles. Where did game developers publish their games? Windows. What was Windows's graphics standard? DirectX. What did DirectX require? Triangles. What did the NV1 use? curves. NVIDIA had built a key for a lock that no door in the market needed. 0.250,000 chips shipped. 0.249,000 returned. A return rate approaching 100%. NVIDIA was in debt. The account was almost empty, and they were dimming the lights to save money. He flew to Tokyo and told Sega's CEO, "We failed. But please pay us anyway." What kept NVIDIA from dying immediately was a Japanese executive. Before the NV1 disaster, NVIDIA had signed a separate contract with Sega to develop the graphics chip for Sega's next-generation gaming console. It was a lifeline, steady development funding, a clear delivery target. If they could build it, the company would survive. But after nearly a year of development, Jensen realized this path was wrong. The architecture they'd built for Sega had a fundamental flaw. Even if they finished it, it couldn't compete with what the mainstream market was producing. Continuing would burn through all of NVIDIA's remaining resources, deliver a failed product, and then bankrupt the company anyway. He faced a choice: keep going, pretend the project was fine, and limp to delivery, or tell the truth now, end the contract, and try to use whatever resources remained to make one more bet. He chose to tell the truth. Jensen flew to Tokyo and sat down with Sega's CEO, Shoichiro Irimajiri, a deeply experienced figure in Japanese business who had negotiated with every kind of American technology company. Jensen looked him in the eye and said, "Our architecture is wrong. This won't work. You should find another supplier." Then he made a request: "Could you still pay us the $5 million agreed in the contract, because it's the only way this company survives." Any ordinary business person, hearing a vendor admit project failure and then ask for money, would have shown them the door. Irimajiri didn't. He later said in an interview that he saw in Jensen something rarer in commercial negotiations than any contract clause: honesty and courage. That $5 million was NVIDIA's lifeline. Jensen brought it back to San Jose, reassembled the engineers who had stayed, and told them, "We're building a new chip. And we have to go fast." They sent the design to TSMC without testing it. The semiconductor industry has an iron law: before a chip goes to a factory for mass production, it must go through rigorous hardware testing. The reason is simple. A modern chip contains billions of transistors and tens of millions of logic gates, the equivalent complexity of building a skyscraper on a silicon wafer the size of a fingernail, where every single wire has to connect correctly. Once you send it to the factory and produce hundreds of thousands of units, any design error means tens of millions of dollars gone. Jensen didn't have time for hardware testing. His team finished the design, ran software simulation, confirmed the simulation cleared, and sent the design files directly to TSMC to begin production. It was an extraordinarily dangerous decision. The gap between a simulation environment and the real physical world contains infinite possible failure modes, and any one of them could render the entire batch useless. The engineers spent the 8-week wait discussing the same question almost every day: did we get something wrong? 8 weeks later, the chips arrived. Jensen picked one up, plugged it in, and turned it on. It worked. Graphics rendered clearly. Speed was there. No errors. No crashes. Exactly as designed. The chip was called the Riva 128. It launched in 1997 and sold 1 million units in 4 months, breaking every sales record in the graphics chip industry. NVIDIA had survived. TSMC noticed. A partnership began and has continued to this day. 1999, he invented a new word, GPU. After finding solid footing, Jensen didn't slow down. In 1999, NVIDIA launched the GeForce 256. The technical specs were remarkable for their time, but the more important thing Jensen did was give it a new name: GPU Graphics Processing Unit. This was not a marketing exercise. It was a redefinition. The CPU, the Central Processing Unit, is a generalist. It excels at working through complex tasks in sequence, step by step. The GPU works on an entirely different principle: thousands of small parallel computing units, designed to handle enormous volumes of simple tasks simultaneously, like calculating the color and shadow of every single pixel in a frame. In a video game, the CPU handles the game logic: where enemies are, how bullet trajectories calculate, how physics engines run. The GPU handles the image: what color every pixel should be in every frame, where the light comes from, how shadows fall. A CPU and a GPU are built to do completely different kinds of work. Jensen quickly understood that this ability to run massive parallel computation wasn't just useful for rendering game graphics. Those thousands of parallel computing units could be applied to any problem that required processing enormous amounts of data simultaneously. scientific simulation, physical modeling, data analysis, in any domain where the scale of computation was large enough, the GPU could be the superior tool. But before 2006, that insight lived almost entirely in his own head. He spent 10 years and hundreds of millions of dollars betting on a market that didn't exist. In 2006, NVIDIA announced CUDA, a software platform that allowed programmers to use GPUs for general-purpose computing. Wall Street analysts questioned the decision for years. The reason was simple: there was no market. In 2006, nobody was using GPUs for AI. There were no large language models, no neural networks, no mature application that needed CUDA. To support it, NVIDIA added extra control circuitry to every GPU chip, circuitry that contributed nothing to graphics rendering and existed purely to enable general-purpose computing, that increased production costs and compressed margins year after year. The analysts weren't wrong to ask, you're building a factory for a customer who doesn't exist. What is that if not burning cash? NVIDIA kept going. 6 years passed. Almost nothing happened. Researchers could use CUDA, but uptake was thin and nothing produced any visible impact. The entire AI field was quiet in those years. Machine learning was still operating at relatively simple algorithmic levels. Nobody believed neural networks were about to become genuinely useful in the near term. The bet Jensen had placed was starting to look more and more like a mistake. 2012, something happened in a small lab in Toronto that changed everything. September 30, 2012. University of Toronto. A graduate student named Alex Krzyzewski, working with his advisor Geoffrey Hinton, submitted a model called AlexNet to the ImageNet image recognition competition. The rules were simple: show the computer a photo, as it to identify what's in it. A dog or a cat. A car or a plane. A hospital or a battlefield. The best error rate before AlexNet was around 25%. AlexNet brought it below 15%. The gap was so large that other competitors assumed there had been a counting error. Even more striking, AlexNet didn't run on a professional supercomputer. It ran on 2 consumer-grade NVIDIA graphics cards. The Hinton team had figured out that training neural networks is fundamentally a problem of large-scale matrix computation, and GPUs handle matrix computation far faster than CPUs. Code written in CUDA could run on graphics cards at speeds more than 10 times faster. When computer scientists around the world saw AlexNet's results, many reached the same conclusion at the same moment: neural networks can work, GPUs are the engine for running them. And CUDA is the bridge connecting the two. The bet Jensen had placed 6 years earlier was suddenly starting to pay off. He personally signed the world's first AI supercomputer and donated it to OpenAI for free. 2016 NVIDIA's GTC conference. Jensen Huang walks onto the stage. Behind him is a machine called the DGX-1, the world's first supercomputer designed specifically for AI training. It held 8 top-tier graphics cards, with total computing power that almost no single server at the time could match. Price tag, $300,000. The audience was confused. The specs were extraordinary, but what could anyone actually use it for at the time? Large language models didn't exist yet. ChatGPT was still 6 years away. Generative AI was science fiction. This was a hammer, but no one could see the nails. After the launch, Jensen made a decision. He personally signed the very first DGX-1 and donated it, without collecting a single dollar, to a small non-profit AI research lab that had recently been founded. That lab was called OpenAI. 6 years later, a descendant of that machine helped train ChatGPT. Nobody is laughing anymore. At the end of 2022, ChatGPT launched. Overnight, the entire world was talking about AI. Everyone was asking the same question: what does it take to build these things? The answer was NVIDIA chips. Training large language models requires enormous amounts of matrix computation, parallel processing, and specialized hardware capable of handling neural networks efficiently. NVIDIA's GPUs had been built for exactly this for nearly 20 years. And because researchers and engineers had spent almost 2 decades writing code in CUDA, every code library, every toolchain, every optimization in the entire field was built on top of it. Switching platforms meant rewriting everything. So Microsoft needed NVIDIA, Google needed it, Amazon needed it, Meta needed it. Every company working on AI needed it. 2023, market cap crosses $1 trillion. 2024, $2 trillion. 2025, $3 trillion. 2026, past $4 trillion, larger than Apple, larger than Microsoft, larger than Saudi Aramco, and larger than the GDP of more than 180 countries. The CEO of the building that once dimmed its lights is now personally worth more than most nations. One thing deserves a moment of its OWN. In 2023, NVIDIA's stock rose roughly 240%. Jensen Huang's personal net worth increased by approximately $60 billion in that single year alone. He became one of the wealthiest people on the planet. Cameras started following him. He wore his leather jacket to every major conference, signed GPUs, and was treated by Silicon Valley engineers like a rock star. His name started appearing in outlets that had never covered a chip company CEO before, but at a university commencement address, he said something that was about the hardest period in NVIDIA's history. I sincerely hope that you will embrace failure. NVIDIA was once a company on the verge of collapse. Our first product failed completely, our customers abandoned us entirely. Microsoft launched a new standard that made us completely irrelevant. At that point, we had 30 days of cash left. The graduates in the audience probably couldn't quite picture it. The man standing at that podium, whose company is now worth more than most nations, once sat in an office building with the hallway lights turned off, calculating exactly how many days he had left. In NVIDIA's story today, there is much worth examining. The early conviction about parallel computing, the decade-long investment in CUDA, the redefinition of what a GPU could be, the early positioning for an AI era that hadn't arrived yet. But if you're looking for the single most fundamental reason beneath all of it, it may be this. In 1996, at the worst possible moment, Jensen Huang didn't quit. When he couldn't find a second path, he put all his chips on the one future he believed he could see. That future arrived. It just came bigger, and harder, and faster than anyone had predicted.